A recent statistical analysis shows that 1 in 1,000 drivers is driving drunk. Due to the high car incidence rates, police officers are asked to breathalyse as many drivers as possible. The tool has a probability of displaying false drunkenness of 2%, meaning that 2% of sober people will be wrongly classified as drunk. However, the breathalysers never fail to detect a truly drunk person. Now, suppose the police officers then stop a driver at random and the breathalyser test indicates that the driver is drunk. How high the probability is that he really is drunk? If you attempted to say 98%, hold your horses. It wouldn't be the correct answer and would actually be a big misinterpretation of what is happening. Let's be patient, look at the strategies we have available and build our solution. We have two options here. We can either write down numbers, try to reduce the problem as much as we can and do some calculations to understand what is going on, or we can recognize that this is a typical example of a conditional probability, where we can apply Bayes' rule. As usual, I will let the more mathematical inclined person to have a go and I will follow the more hands-on approach. We know that 1 in 1,000 drivers is drunk, so let's assume we have exactly 1,000 drivers and that one of them is drunk. Let's now test all of them and see what happens. The breathalyser will not fail to detect the drunk person, so we can already classify it as a true positive. And we also know that we won't have any false negative. However, we know that 2% of sober drivers will be misclassified as drunk, what we call false positive. In our example, this corresponds to 2% of 999, which we can safely round to 20 people. Finally, the remaining 979 will be correctly classified as sober, the true negatives. Okay, time for some maths. The probability of someone tested drunk or positive to actually be drunk can be calculated as the ratio of the number of outcomes that produce a given event, in this case really being drunk, so one case, to the total number of possible outcomes, testing drunk, so 21 cases, 1 true positive and 20 false positives. This might be surprising, but it is indeed the correct answer, not even 5%. In other terms, this person still has a 95% probability of being sober. You might even question the point of performing the test. By the way, if you use Bayes' theorem, you can get the right answer with just one formula. Let the proposition A be the person tested positive to the breathalyser and B the person is drunk. Then we have that the probability of B under the condition A is equal to the probability of A under the condition B times the probability of B divided by the probability of A, which we can compute using the law of total probability, stating that P of A can be obtained as the sum of P of A given B times P of B and P of A given not B times P of not B. Sounds much more complicated than it is in reality. Replacing all numbers gives us the same result as before. If you're still puzzled by this result, you're not alone. This is known as the false positive paradox, or, to use a better expression, the Bayes rate fallacy, and can be applied in many situations where the occurrence of the phenomenon we're trying to detect is so rare that even a small rate of false positives can become very significant. In medicine, we refer to the specificity of a test as the ratio of true negatives over all negatives, which in our case was 98%. And often we use this as a metric of how accurate the test is. But it is important to keep in mind that without knowing the prior probability, it is actually completely useless. If you're interested in the subject, I strongly recommend you watch a video from 3 Blue 1 Brown, for which the link is in the description down below. He explains in great detail how the role of the specificity is not to give an estimate of how predictive the test is, but rather update a prior distribution, which in our case was just 1 in 1,000. Did you solve the riddle, and how would you classify it? Let me know in the comments down below if you fell in the trap. Hopefully this also gives you a chance to understand how to more carefully interpret the data when we talk about test accuracy. I hope you enjoyed the video. If you did, make sure you press the like button and subscribe to the channel to get notified when our next riddle is out. I will see you in the next video. I am Yuri and this is RiddleBear, the channel that will help you develop riddle solving skills and be able to solve riddles you didn't think you were capable of.